My name is Jim Hendershot, and I would like to introduce a tutorial lecture series that I've prepared on how to design three kinds of electric motors. These lectures consist of 37 different lectures, and the first 15 cover the topics that are common to all three motor types. These pertain to the sizing of these three types of machines, the active magnetic material selection, and the actual design of the stators and what are the characteristics that are required for these common stators. Then there's 7 lectures on the detailed design of the rotors for induction machines using the stators described in the first 15 lectures. The next 4 lectures describe the design techniques for reluctant synchronous motors. And the next 6 slides or lectures contain slides that are used to describe the design of permanent magnet rotors used in brushless machines that either have surface permanent magnets mounted on the rotor or interior permanent magnets mounted inside the rotor. And finally, there's 5 additional lectures have been added as general topics that apply to all these machines, relating to the thermal condition of the motor, how hot different parts of the motor get due to the losses inside the motor, and then the mechanical design aspects, including shafts, bearings, frames, housings, some manufacturing techniques that are used for these different machines, and finally there's a lecture on the future challenges for engineers for designing machines of the future. Now, let it be understood up front here that these lectures are assumed, they're designed for engineers who have a basic understanding of the theory of electric machines. It's not intended here to reteach that material. This material is intended to supplement the knowledge of engineers so that they know how to apply their theory to the practical design of a machine. So the first lecture is about the history and introduction of various machine types and how they evolved from their original inventions 150 years ago. The first known machine that we have record of is a very unusual machine, and it's worth looking at because we have these inside of our body. It's in every body of water. These little motors are in sewers. They're in most kinds of liquids and solids around organic solids on our entire planet. These are microscopic bacteria propulsion motors that propel the bacteria that's in all living matter. It allows them to propel themselves at will around the media that they survive in. And it's very interesting to look at because if you look at this diagram with the description of the components and this actual plastic model here, you see that all the components in this bacteria propulsion motor are the same ones that are in the motors that we're going to study. We have a shaft, we have bearings, we have a rotor, we have a stator. The rotor is rotated by electromagnetic means, and it rotates this shaft, which goes through this universal joint called a hook into this flagellar element, which is similar to the tail of a fish. And so when this thing rotates, it's able to go forward and reverse and to propel this bacteria at will any direction, forward and reverse inside the media. So, and this model certainly looks like some modern motors. There's a famous museum in Bellingham, Washington called the Spark Museum of Electrical Inventions, and here we see there's a big picture on the wall there that shows a composite photograph of the inventors and the people in past history that contribute to these electric machines and electric energy, and you see down here some early examples of their accomplishments. Faraday and Tesla are two of the most famous and the most important contributors to this technology, as we all well know. And here's a picture of a photograph of one of the early motor samples that is in that museum. For 150 years we've had electric motors, and the first ones were developed in the 1800s, and they were middle 1800s, and they were powered by DC power, by lousy batteries. And shortly thereafter, Edison and his people in his research lab in Menlo Park, New Jersey, developed a lot of different kinds of DC machines, including generators that operated from DC grid power. The first generating systems in cities in New York was a DC grid. But then Tesla patented the AC motor in the AC grid system in the late 1800s, so the AC power became the standard grid of the world over the last 150 years. So consequently, most motors are AC induction motors, but they run off the grid, as we all know. Here's a couple of examples of an old classroom motor used to teach motor technologies, called the St. Louis motor. It's got a battery and a little wound rotor there. And then this is a modern dyno kit that's used by the University of Minnesota, as a matter of fact, and other universities around the United States, if not the world, to teach the characteristics of different kinds of machines. This is a permanent magnet generator, uses a load. There's an inline torque transducer. There's an encoder, a tachometer, used for a tachometer for RPM on the back of this. And then you can mount different test motors here to test them and study their characteristics and the control characteristics. But the first 75 years of the last 150 years, motors were either powered by batteries or DC voltages from an MG set, motor generator set, or the other family of motors, they were powered off this AC grid. In the United States, the sinusoidal frequency of the three-phase power was 60 hertz. Most of the rest of the world was 50 hertz. And so we had two classes of motor that were powered by two different power sources. They were either AC or DC motors. There is one unique motor, a series wound commutated motor it's called, that will run on AC or DC power. However, in the last 50 to 75 years, or principally since the Second World War, after the invention of transistors and microprocessors, these same motors, these two classes of AC and DC motors, evolved into hybrid versions of themselves as they became powered and controlled from inverters, where you could achieve variable speed. You could change the frequency and change the voltage, and you can actually put all sorts of feedback systems on the motor, such that you could control number of revolutions or part of a revolution, that you can for what they call a servoing for incremental motion. A popular motor that came out of the AC synchronous family is called a stepping motor. There's VR, variable reluctance motors, stepping motors, permanent magnet stepping motors, and hybrid stepping motors. Then there's the PM brushless motors, evolved out of one of those DC motors that we saw in the last slide. The DC motor that has permanent magnets in the stator, if you just reverse the rotor in the stator, you put the magnets on the rotor and the windings in the stator, that was called a PM brushless motor. But later, as we'll see, when inverter designers started to run that motor from a slightly different power control source, he changed the name of it from a PM brushless to a PM AC, or a PM synchronous machine. Then there's the classic AC induction machine that for the first 75 years was powered off the grid. When you put an inverter on it, though, you can control the voltage and frequency two different ways, open loop or closed loop, and so we have variable speed induction motors. And all three of those motor types are similar in that they have a magnetic field in the stator and the rotor. But we come down here to these next two. These are reluctance machines. They're called salient pole machines, and there's only one magnetic circuit that's always in the stator, and the rotor of the magnetic circuit becomes part of the magnetic circuit of the stator, but this part is mounted in bearings, so rotation results. The switch reluctance motor has salient poles in the stator and the rotor. The reluctance synchronous machine only has saliency in the rotor itself. You can configure all of these machines three different ways: radial, axial, or transverse flux. I think those definitions are almost self-explanatory, but we'll look at some in some future slides. The Small Motor Manufacturers Association, called the SMMA, is an association of motor manufacturers and motor users and motor distributors and anyone else that's interested in motors. And so they've developed this family tree. You can see there's three categories. There's the AC family, the DC family, and the electronically controlled family. And those are the same three families that we've described in the previous slides. The basic induction motor that has been used for the first 75 years has evolved into these other kinds of machines there. And then the DC motors that are powered by magnets or DC power supplies, they've evolved as well and become, they've all had new names and new versions, and they wind up in the family of electronically controlled motors, as you can see there. It's worth studying, not so useful for the detailed design, but it's good to have such an overview of how these motors evolved. Let's start with the definition of electric machines. Let's define electric machine includes a motor and a generator. An electric motor converts electromagnetic energy from some external power source, this can be AC or DC, into mechanical energy across the air gap between the rotor and the stator, causing the rotating part to turn, applying a torque. And how fast you apply that torque equals the power of that machine. Now, if we reverse the power flow, instead of the power flowing from the electric power source to convert it to mechanical energy, if we start the power flow from the shaft by rotating the shaft with some prime mover that could be an internal combustion engine, a wind turbine, a tidal turbine, ocean tidal or sea turbine, or a gas turbine, a jet engine, and you rotate the shaft, then you can have the energy flow from the shaft to the stator and convert that mechanical energy into electrical power, and that's how all our power plants work all over the world. They're basically the same type of machine, it's just a reverse of the power flow. All of these machines require magnetic fields. The first ones that we talked about need a magnetic field in the rotor and the stator. The reluctance machine only need one magnetic field, but these magnetic fields have to have a source. Well, what are the sources? Well, the Earth has a magnetic field, the North Pole, South Pole. We're still trying to completely understand where the magnetic field of the Earth comes from. But and that field's not very useful as far as we know today for motors. So then you have a magnetic field that exists between the planets, what keeps them in orbit. And then you have magnetic fields created by nuclear activity. Then let's get down. That leaves us with electromagnetic fields or electromagnets and permanent magnetic fields from permanent magnets. Those are the two we're most familiar with and the ones that we need to consider to make a motor rotate. There's also superconducting magnetic fields. They're quite interesting to study. And certainly, I suppose in the future, there will be superconductivity motors in wider use than they are today. The only trouble is you have to keep them at very cold temperatures to keep them as superconducting. But let's first think of the magnet. If we've been taught since we were children that Did you never get anything for nothing in this world? Did you have to pay for everything? Well, a permanent magnet is as close as you get to getting something for nothing. It's really quite an amazing phenomenon when you think about it. Same as you can start with that phenomenon, the amazingness of that phenomenon, just by the magnetic fields in the earth. Our bodies aren't magnetic, and yet we stick to the earth. We don't fall off the earth, so the magnetic field keeps us there. But in the case of the permanent magnet, there's special materials that are known as ferromagnetic materials. And if you take one of these magnets, the names we go by are samarium, cobalt, neodymium, ferrite magnets. Those are the common names of magnets. We all know that. If you have to buy the magnet, and you have to pay for some electricity in a magnetizing fixture to magnetize it. But once you magnetize it, you get a force field coming off of this magnet going from the North Pole to the South Pole. You get this force field that basically lasts forever. The only way you could destroy it is to overheat it or demagnetize it with some external electromagnetic field. So that comes pretty close to getting something for nothing. Now, this force field is something you can't even see unless you put a piece of paper over the top of the magnet and sprinkle some iron filings on it, and then you see this pattern of flux lines here. And the mathematically, we can't see this, but we can use mathematics and display it graphically using what's known as a finite element solver, and we can plot these flux lines in an equal potential plot, which we'll see some of those later. So this force field is something you can't see, and this is what happens in the air gap between the rotor and the stator, and that's where this conversion of energy takes place, through those lines of flux in that from the magnetic field in that air gap. Now let's look at we've all studied the theory of why a current flows, when you have a current flowing in a conductor, why there's a magnetic field around it, the right-hand rule and all that. We've studied that. But let's think about it in a physical way and look at a picture and try to get a feel for what's going on here. Let's take this conductor and let's wrap a bunch of turns into a coil like this. You could wrap this around a broomstick handle and pull the broomstick out of this coil of wire. And so if you put a voltage across there, you get a current to flow inside that wire, and you get flux, a magnetic field that rotates toroidally like a donut around each one of those conductors. So when you collect them all together, you have a toroidal or a donut shaped magnetic field that goes around that coil that you see there in this picture, and it's quite concentrated on the inside, but it's not concentrated on the outside, and that's because this magnetism flows through air, and the permeability of air is unity. That's permeability is the measure of a material or substance to collect and transmit magnetic fields. So if we replace this air with this iron core that you see in this picture here, we have iron core material varies from stainless steel is magnetic. The magnetic stainless steels, the 400 series magnetic stainless steels are magnetic, and they have a permeability in the range of 250 to 350. But if you use the very pure Swedish iron with no impurities in it at all, it's just pure iron, then you get permeabilities up to 6,000. So those kind of materials are very happy to collect all of this flux. There's our coil. We've shortened it a bit. We wound it so all the wires are punched together. So you got all these turns wrapped around here with the steel inside of it, and we've also put an air gap in here. So all these lines of flux that go around here generated by that coil, and it doesn't take much ampere turns or turns times the current flowing to magnetize this iron, but it takes a lot more to magnetize this air gap, to get the lines of flux that are flowing from the coil in the core, jump across the air gap and go to the other side. But this is where this air gap is in the motor between the rotor and the stator, isn't it? So let's review the magnetic flux linkage that comes from that previous from this generation of the magnetic flux. And let's see how that relates to motors. There's two categories of electric motors. There's non-salient pole and salient pole machines. Those are the only two categories there are. Now, salient pole machines exhibit an attractive tangential force in the air gap between the rotor and the stator. And we'll look and see what that really means pictorially later. Non-salient pole machines exhibit an attractive tangential gap force also, but they also produce a repulsive gap. Repulsive, not repulsive, repulsive gap. And this is like if you have two magnets, one in each hand. If you have a north pole in your right hand and a south pole in your left hand, and you bring those close together, if they suck together or attract to each other, that's the attractive force between two magnets. One, in this case, we described two permanent magnets, but one could be an electromagnet. Now, a repulsive is in the case if you turn one of those magnets over so you have a north pole facing a north pole or a south pole facing a south pole. You try to bring them together and they won't come together. They will force themselves apart. Well, you get a force from both of these. You get an attractive force or a repulsive tangential force. So the torque that's produced on the shaft is produced by by those two forms of flux linkage for motoring, and the same thing happens if you're generating. You have the reverse power flow and you have voltage produced from those air gap forces. What are the motor types that we're going to study here? The original motors. These aren't the motor types we're going to study. These are the motors that evolved through the past 75, 150 years. The original motors were called PM brush type motors, and they had the magnets on the stator and the windings on the rotor, and they were mechanically commutated with brushes and commutators. And so when someone got the bright idea to reverse those motors, put the magnets on the rotor and put the windings on the stator, they came up with because they didn't have brushes anymore, they called them brushless. And because they were powered by switching DC, just like the commutated motor was, the commutations did the DC switching, but in the brushless they did transistors to do the switching. So they would. That's why it was called a brushless DC motor. But then, as the years went by, they started to drive these motors differently, and instead of switching DC, they would apply sinusoidal AC to all three phases instead of two phases at a time, like they did with the brushless. But if you take let's go back to this statement here. If you take these motors and you spin them like a generator, you drive them. Take a motor and stick a shaft in a drill press and spin it with a drill press, and look at the voltage across the lead wires, and put that output on that on a scope and see what its shape is. You can see its amplitude, frequency, and its shape on an oscilloscope. So if it's square, it's thought that a brushless DC motor needs to have a square wave back EMF, and a sinusoidal driven motor is thought that it needs a sinusoidal back EMF. Now that's not necessarily true. You can drive either. You can use a brushless drive or a sine drive to drive a sine motor or a square motor. They're really the same motor, and in reality, any brushless motors that you design, the actual back EMF wave shape is neither square nor sine. It's somewhere in between. And there's effects to those, which we'll discuss later. But the inverter people who took the brushless motor that was formerly driven with a 6-step drive with 2 phases on, switching DC voltages across the terminals. As soon as they applied their drives that they use for induction machines using hysteresis control or D and Q axis current control, they changed the name of these motors. They changed the name of them to permanent magnet synchronous machines because they were running them like synchronous motors, and they were applying AC current to them. So they changed the name of the motor. So a lot of people thought that they were different motors, but they're not. They're the same motor. They just have different drives. Here's a kind of a useful chart, not for design, but just for background, to show kind of the two families or categories of DC motors and AC motors. The motor engineer, he looks at the motor different than the control engineer. The control engineer uses terminology and describes and things and models the motor using MATLAB Simulink models that model the motor as a black box that he needs to use for his control theory to get his motor and drive commission and getting it all up and running right. But those considerations aren't near as useful to the motor designer. The motor designer's got to figure out how many turns to put in the machine and how big to make the rotor and how to design the lambs and how to insulate the machine and how to commutate the machine and things like that. So he looks at the motor totally different than the drive guy. The 3 motors that we're going to study in this lecture series are described here. There's the IM, which is the A&D induction machine, not the ones that are powered by the grid, but the ones that are inverter driven. That's what we're going to emphasize is the details of why and how you have to use the right rotor design if you're going to run an AC induction machine from an inverter. And then we're going to take the same stator or a similar stator from an induction machine and replace the rotor. The squirrel cage induction rotor, we're going to replace it with a reluctant synchronous rotor and drive that with the same type of inverter and see what we have to do to optimize the rotor for that. And finally, we're going to use the same stator and we're going to put a permanent magnet synchronous we're going to put a permanent magnet rotor in there to run it as a permanent magnet synchronous machine and see what we have to do to optimize the rotor to get the best performance. And best performance means the highest torque density at the lowest input power. That's what best performance means. Efficiency, power factor, things of that sort. What are the similar characteristics of these 3 machines? Why have we picked these machines? Well, because all 3 use the same stator core designs and windings. They can use the same laminations. The manufacturing infrastructure for the stators are the same. The choices of active magnetic materials that are used in the stator, the insulation systems, the whole everything about the stator is common to all 3 of these types of machines. How are they controlled? Also, all 3 of them can be controlled with Q and D axis current control with just different software. So this makes it these motors very attractive for the same company to be involved in, to use the right motor for the right application, because there's so much cross-pollination in all the technologies that are involved and the manufacturing infrastructure involved. The main difference of these 3 machines is each one requires a special rotor configuration. And finally, to summarize this particular first lecture and introduction, we see here a picture of the 3 cross-sections of these 3 machines. We see that the stators are pretty much the same. Well, the slots are deeper, shorter, narrower, wider, different number, but basically it's the same stator. The difference being the 3 rotors. The induction machine here has teardrop slots in it, which is cast with either copper or aluminum. The reluctance machine has a strange shaped rotor punching that has passageways outlined in blue here, these passageways are where the flux wants to go, and the flux does not want to go where the light colors are. That's air. Those are flux barriers. You could put magnets in there, but so the flux wants to go this way, not that way. So the saliency is this. This is a salient pole. Now the permanent magnet machine, the one that we show here, uses the same kind of stator as the other two, but the magnets are buried inside the rotor. And so there's 2 magnets per pole. These are red ones are north poles, the blue ones are south poles. And we have this soft laminated pole in between here. That's kind of like the salient poles on this machine. So this particular IPM, it's called, internal magnet permanent magnet machine. This is a permanent magnet synchronous machine with IPM rotor configuration. The magnets could have been on the surface up here, but they're inside, and they're shaped in a V, so we can spread them apart and get this soft iron in between, which gives this saliency. So those are the machines that we're going to study.